a screencast for PowerPoint that I would be presenting in class about how to use position time graphs and figure things out about those. So I'm going to play this from the start. Sorry about the delay. Not sure what. So if we look at these graphs, we've got graph A here and graph B. Which object's moving the fastest in graph A? Well, hopefully you recognize if they travel in the same amount of time, say 4 seconds, that object 2 and 1 start at the same point, but object 2 travels a greater change in position, it's going to be traveling faster. So we can use that by looking at the slope of object 2 and object 1. So the slope of object 1 is about 1.45 meters per second. The slope of object 2 is going to be steeper than that, so it's going to be a greater number. So that's going to end up being about 2.6 meters per second. Now let's take a look over here for graph B. We do the same thing. If you look, object 1 here is the same as it was in the first graph, but object 2 is not. So object 2 would end up being less steep, by the way. Now, for position time graphs, we would want to think about velocity time graphs coming from those. So we would end up putting units on our axes. If we have a constant velocity, we're going to have a line with a constant slope here. Why? Because this is looking at velocity versus time, not position versus time. So the object, and I don't know why those lines aren't quite straight, but the object with the higher velocity is going to still be a horizontal line, but it's going to be higher up. If we end up having something where we've got a negative velocity, our line would actually just be below 0. All these are above 0, though. The slopes of the velocity time graphs would tell us if we have acceleration. So for these velocity time graphs, there is no slope, so there is no acceleration. So again, we're going back to that, no rise, something like that. Acceleration is a change in velocity divided by a change in time. So if we look at this position time graph, we've got object A here. Oops, I want to actually go back to that, so let me escape that for a second. We could figure out the velocity in this region by looking at the change in position divided by the change in time. So 60 minus 0 meters over 10 minus 0 seconds would be 6 meters per second. In this region, we would have a speed of 0 or velocity of 0 meters per second. Here, we're going from 60 meters per second to negative 40 meters per second. So our change in position is negative 100 meters. That's negative 40 minus 60. And all that is divided by 25 seconds. Why? Because I start this interval at 15 seconds and I end at 40 seconds. So I could use that to calculate the acceleration or the velocity. And here I would have a positive velocity because I've got a positive slope. So there's a few ways we can describe motion. We can have a position versus time graph, we can have a velocity time graph, a written description, and then we can have a motion map. So in this region here, we've got A, B, and C, 3 regions. A is a constant velocity away from the reference point, so that's a positive velocity. B is stopped, there's no change in position. C is a constant velocity back toward the reference point. It's a negative velocity, and it'll be moving faster because it's steeper. So A, positive velocity. B, no velocity. C, negative velocity. Now there is something wrong with this, and I'm going to have to try to fix that. This should be further down below because it is more negative than this one is positive. So again, we would have shorter arrows here, 3 dots where it's not moving, and longer arrows here. Again, I think these should be the same length. So we've got another one here, and you may want to think about what that would look like. Moving toward the reference point, stopped. Moving toward the reference point, moving at much greater speed. Okay. I'm going to move kind of quickly through here because these are pretty similar. Again, you can pause the video if you'd like to look at examples. Here A is stopped, B is moving, C is also stopped. The slope of a position time graph represents velocity. The slope of a velocity time graph represents acceleration. So if we're changing velocity here, that means we're speeding up. In this region from E to F, we would be slowing down. That means we would have a constant, either a positive acceleration here or a negative acceleration. Sometimes people use the word deceleration for negative acceleration. I don't know if I like that. We'll do some graph matching in class. Using the coordinate system with the origin far left, far right positions. So left is positive positions are increasing to the right. If we had an object at rest, what would that look like? Something like that. If we had an object moving away from the motion sensor with a constant speed, so it's moving in the positive direction, something like that. Object moving toward the motion sensor with a constant speed, something like that. It's a negative velocity. This is a positive velocity. So you should be able to let me know what a steeper slope means. So if we look, an object accelerating away from a motion detector starting from rest. If it's accelerating, the position time graph won't have a constant slope. If you're going faster and faster and faster, that means your rate of change of position per unit time is going to increase. So your slope should actually increase. It's kind of a weird line there, but that's kind of what it would look like. Very nice. We're going to end up doing some of these as an activity or as something to think about. So here's the data points. They both start at 0, 0. Object 1 ends at 2.5 seconds and 100 centimeters. Object 2 at 2 seconds and 50 centimeters. Here, these both start at 0 seconds, but object 1 is starting at 80 centimeters, going back down to 0 after 2.5 seconds. Object 2 starting at 0, going to 50 centimeters in about 2.25 seconds, I guess. Pick 2 points on the line of best fit, mark them on the graph. Doesn't matter exactly where they are. This is just making sure you know how to do this. But once again, the slope is the change in y values divided by the change in x values. In this particular case, it's going to be 40 minus 20 meters over 4 minus 2 seconds. That's going to be a positive 10 meters per second. For this position time graph, pick 2 points in the line between 0 and 5 seconds, mark them on the graph. Again, we can get the slope that way. It's going to be 2 meters per second. But now during the second region, here, the graph has got a negative slope. And so therefore, it should end up having a negative velocity. And you either have negative up top, positive on the bottom, positive up top, negative at the bottom. Either way, you would end up getting a negative velocity. We're going to end up doing a simulation with these motion maps on the physics classroom. So we've done these already. I think the same size arrows represent constant speed. We've talked about that. Arrow to the right, positive velocity. Arrow to the left, negative velocity. If they're going faster, they're further apart. I wouldn't say an increase in speed. I'd just say it's faster. So they're going to the left, pointing that way. That would be a negative velocity. If we have a more complicated motion, we would have something like this. At least at first, we're going constant speed toward the right with a positive velocity. We're stopped for a few seconds. Then we're going to the left with a slower constant speed. So we would think of this third region as a negative velocity. So if we look at motion maps and position time graphs, here we should have a positive velocity, zero velocity, and a negative velocity. So what would that look like? At least initially, we're going from 0 to 4 meters. We're going to be stopped for a little bit. And then we're going from 4 back to 0 meters. Not quite as steep, so the slope isn't quite as much. And therefore, we've got more arrows, and the arrows are closer together. So if we have a motion map here, what could our position time graph look like? If we start at this, we're starting at a plus 5 meters, so I could better label this up to 5. We're going to then be going backwards. So we're going back to 2 meters. Looks like it's taking us 3 seconds to do that. Then we're going to be at rest for a couple seconds. Then we're going to go 2 seconds again backwards. We're going to rest at 0 for a couple seconds. Then we're going to go really fast back to 5 meters. It looks like that takes, I would say that probably should take 3 whole seconds or so. It may not take quite that much. So these are things we're going to look at with the runners and so forth for cyclists A and B. Drawing a motion map for both of those for cyclist A. Starting at 0 meters. Cyclist B. Going a bit slower. I would move this to the right a little bit because it looks like it starts above 0. And those words are correct. Here, we've got one positive velocity, one negative velocity. Putting in some numbers here. Object A should have a positive motion map. Object B should have a negative motion map. Again, I'm not sure if I like this because I think B is moving slower, so I would say the arrows would be closer together. And I think that is good for what we're doing today. So I'm going to get out of this. That is plenty of talk about things. Holy cow, that is a lot. At any rate, we're going to stop that now. Hopefully you understand the ideas of how position time graph, velocity time graph, and motion maps relate to each other.